Oh, what's the time? 2:02. Oh, maybe I should get started, hey? A nice concept to explain. Okay, at any time, by the way, Jasmine, I'm not sure I could hear your voice, but if you say something in the chat, I can read it. Like if you want me to cover anything or talk about it, then I certainly can. So I don't want to just mindlessly go over questions from the exam if I can avoid it, because that's not the most engaging thing in the world. So Shoya over here has asked the question to explain Heisenberg's uncertainty principle. So I can give a rough explanation. So I'll just have the attendance form QR code over here. And I'll start with an explanation of Heisenberg's uncertainty principle. So what do you know of quantum mechanics? Small things. Sure. So that's a good start. Yeah, things that are small and things that are quantized, whatever that means. So in classical mechanics, you have a particle, right? And your particle is described by two things. Its position, x, and, or if we just restrict to one dimension, let's make it not a vector, and its velocity v. Yeah. So particles have well-defined position and momenta. Now, it turns out in quantum mechanics, particles are not described by this. In quantum mechanics, a particle is described by a wave function, which depends on your position, psi of x. So this is like the x-axis. Yeah, we call this a wave function. And the wave function can be a complex number in general. So its value at each point it's not necessarily just real, can be complex. So if, so the state of a particle is described by a wave function, which means somehow from this function, it'll be very nice, right, to recover a little bit of classical mechanics. So it would be nice to, if we could, derive, like, look at a wave function and be like, that's what the position of the particle roughly is, or that's what its velocity or momentum roughly is. Are you looking at lecture notes or something? Yeah. So let's talk about position first. Yeah. The interpretation of the wave function is that when you take the absolute value of it, psi of x, and square it, then that gives you the probability density of it. So psi of x by itself is just the wave function. It is just the state of the particle. So it turns out, okay, if we can only ever measure psi of x squared so far, right? You think, why do we need psi of x originally? Why not talk always about just psi of x squared? Well, it turns out like the complex, so the phase in complex space is actually useful. For instance, it tells us about the momentum, but we'll get to that. So already we see, I'm talking about probabilities here, which is a bit stunning because, right, in classical mechanics, you don't have probabilities. It's a particles here, and that's it, right? But in quantum mechanics, what this tells us is that, so if I plot psi of x squared now, it might look, something like this. What this means is I have my particle that's in this state, and if I want to measure its position, what this tells me is I'm very likely to measure its position, like somewhere between here, and I'm like a little bit likely to measure it out here, and then a bit further out, basically I have no chance. So this is the interpretation of the wave function. The wave function tells you, or at least when you square it and take the absolute value, the probability that you'll find where a particle is. So the y-axis over here is psi of x squared. Yeah. So hello. Good to have you. So now, if I were to ask you, next question, what's the velocity of this particle described by this wave function? So you're reciting the uncertainty principle to me, but somehow in this wave function, we encode the momentum of this particle. Right, so somewhere in there, momentum is hiding, but just where is it? And it turns out, just by the way, you don't need to know this for your course, but it turns out the momentum, you get the momentum of the wave function as a kind of multiplication. So it turns out is minus I d psi dx. So it turns out if you differentiate it and then have a minus I in there, oops, then the number that you get out in front of it by differentiating it is the momentum, basically. So if you're familiar with linear algebra, this is a kind of eigenvalue equation because you it's like you hit your wave function with something, in this case it's a differential operator, and you get a number out in front. So it's like you hit a vector with a matrix and it becomes a number times that vector. That's an eigenvalue thing. So this turns out to also be an eigenvalue type problem, but you don't need to know that for now. Anyway, point is, the slope of this thing, so what happens when you differentiate it, is what gives you the momentum, basically. So what we have here is, so we have a way of getting the position, we have a density for this, and we have some idea of getting the momentum. It turns like how much it changes. So now let's talk about the uncertainty principle, yeah? So the uncertainty principle basically says, I'll write it down, delta x, delta p is greater than or equal to h bar on 2, yeah? So what is delta x? Delta x is basically the spread of how far apart you're likely to find your particle. So if my probability density is this wide, then delta x is about this, yeah? And you can think of the spread in momentum, as like the spread in possible values you can get of your derivative. So let's have some comparisons, yeah? So I'm going to draw a wave function. I'm going to draw a wave function that's, arrange for the slope, exactly. So I'm going to draw a very localized wave function, and I'm going to draw a very spread out wave function. You can see in this one that the derivative gets very large, right? So if I plot psi here, and if I plot d psi dx here, then d psi dx is 0, and then it like blows up, right? And then it becomes negative again, right? And then it's 0. Crappy drawing. And then in this one here, it's a very gentle slope, yeah? So the d psi dx is more like just it goes up a little bit, and then at the peak it's back to 0, and then and then on the way down it's just a bit down again and like this, yeah? So in this case here, you can think of this variation in the slope as delta p. And for this one here, we have a small delta p. And this one here, we have a small delta x. And this one here, we have a large delta x. So this is basically the Heisenberg uncertainty principle. So if delta x is small, then delta p will be large. And if delta x is large, then delta p will be small. Yeah, so exactly. So it's set up in such a way that it will always be greater than or equal to h bar over 2. Now, you don't need to know this for physics 1b, but you can actually write down this function more properly. Have you ever heard of a Fourier transform? That's okay. Yeah, so it turns out Fourier transforms, if you start with the wave function for your thing, and you take a Fourier transform of it, it will give you the momentum density function, it turns out. But anyway, you don't need to know this is physics 1b. But anyway, hopefully that explains the Heisenberg uncertainty principle, right? If it's spread out in space, it's confined in momentum. And if it's confined in space, it's spread out in momentum. Schrodinger's equation. So what do you want to know about Schrodinger's equation? Everything. Start from scratch. Okay. So, all right. Schrodinger's equation. So in classical mechanics, right, you have an equation of motion, right? An equation that tells you what your particles do. What is your equation of motion in classical mechanics generally? Do we know? F equals ma. So what this tells you is if you know the force on your particle, then you know the acceleration it will undergo, and therefore you can figure out what trajectory it takes. So what Schrodinger's equation basically is, it's the F equals ma of quantum mechanics. It is the equation of motion of quantum mechanics. So as soon as we, in classical mechanics, right, we have our particles, which are at points described by their position and velocity. But in quantum mechanics, now they're described by wave functions. So it doesn't really make much sense to talk about forces on something that's spread out in space, right? So the idea is we have to start thinking a bit more creatively. And it turns out, in order to generalize to wave functions, which are spread out in space, it's better to talk about potential energy and potentials rather than forces. And in case you remember, the force on a particle, if it's in a potential, is minus dv dx. In case you remember this, hopefully this might be familiar from physics 1a, right? Because if you're on a ball that's rolling down a hill, right, the potential goes down here, right? The force will be to the right because minus dv dx will point to the right. Anyway, so Schrodinger's equation is the equation of motion for a quantum particle. So let's just write it down. Yeah, we have e psi equals minus h bar squared on 2m d squared psi dx squared plus the potential energy, which might depend on position, times psi. So this is Schrodinger's equation. So you might recognize here we have d squared psi dx squared, and I told you before that momentum is, or minus I, there's an h bar in there, d psi dx. So what this is really saying is the energy of the wave function is the momentum p squared on 2m of the wave function plus this. So if you factor out the wave function, it's saying energy is kinetic plus potential. And if you want to make this an equation of motion, we actually replace energy with with I h bar d psi dt. But in first year, you don't do this. So if you want to turn it in an equation of motion that depends on time, you would have minus I h bar d psi dt equals this stuff here. But instead, what you do in physics 1b is you want to work out what your particle looks like if it has this energy. Yeah. So basically, the way it then works is, so this is Schrodinger's equation. It tells you what your thing will look like. So what you'll do is you'll get given a potential. For instance, you'll be given an infinite square well. So the potential is 0 in here and v equals infinity out here. So what this means is your particle can only live between like the two sides of the potential, say between x equals 0 and x equals L. And when you carry through Schrodinger's equation, you'll find out that you only have a certain number of like allowed states. So you'll have a state with the lowest energy that looks like this. Psi of x will look like this. And then the next one will look like this. And then so on and so forth. Y-axis is psi of x, your wave function. So hopefully, like you would have seen in class how to work through working out. Have you actually covered any of this in the lectures? Only in tutorials. So do you even know if this is going to be in your exam? Because I'm thinking it's unlikely.
The questions were mostly based on deriving Heisenberg transfer configuration. I didn't really touch on with equation.
Okay, so you're feeling scared about it because you don't feel it's been adequately covered in the tutorials.
For sure, we have covered a couple of questions for Heisenberg transfer, and it's pretty straightforward.
Yeah, Heisenberg uncertainty principle is usually like straightforward. It's, you know, you're like, yeah, that's normally all it comes down to. Or sometimes you see the other version, which is delta E, delta T.
But that's it. We don't, that's all we do for Heisenberg transfer.
Yeah. Okay. So we can all work through one. There was an example in this past exam that I can work through if you'd like. We can work through it together. We can all figure it out. Yeah. All right. 2. If it loads. All right. So let's work through this question, hey? A one-dimensional infinite potential well contains a single electron. Sketch the form of the wave function in the ground state and the first two excited states. So do we know how to start? Do you have a rough idea of what to expect? No. All right. So okay, so it probably won't ask you to do this, but I guess it would still help to understand what's going on. So a potential well with width L equals 0.6 nanometers. So I'm going to draw it like this. So here is x equals 0, and here is x equals L. Now, when the potential up here is infinity, we know that you're not allowed to have your particle at all. You have 0 probability of finding it, right? Psi equals 0. So I'm going to draw my wave function out here. So I know it's going to be 0 out here because I have no chance of finding my particle, yeah? Okay, so now let's figure out what our wave function will look like inside here. So for this, we turn to Schrodinger's equation. So again, you'll find it in your formula sheet, but to remind you, it is E psi equals minus h bar squared on 2m d squared psi dx squared plus v of x psi. Now, inside the well, can we make any simplifications? Is there anything that's 0? The potential is going to be 0. Great. So we don't have to care about this term at all. Yeah. So we have, so this is a differential equation that's actually quite friendly now, right? So I can take these constants all over to one side, and I have d squared psi dx squared equals minus 2me over h bar squared psi. So do you two know how to solve this differential equation? No? So do you know any functions where if you take two derivatives, you just get out minus times minus a number times that? So trigonometry? Yeah. In fact, have you ever seen the harmonic oscillator before? Like, you know, MMA equals minus KX. So X double dot equals minus K on MX. It's exactly like this. Yeah. So yeah. So what's the general solution to this? It's psi equals some constant A times sine of, and I'm just going to call it K here, KX plus B cos KX, where here K is equal to square root 2me over h bar. So would you have to derive this? Yes, probably. Possibly. Like, it's expected that you should be able to solve equations like this in the exam. Right. And you'll note now we have two unknown quantities, right? We need to figure out what A is, and we need to figure out what B is, because they could just be anything. Our differential equation doesn't tell us. So, fortunately, we have two things that we can use to nail down A and B, right? We have two unknowns, but we have two conditions, important conditions that a wave function must satisfy. Do you have any ideas what they might be? So I'll give you a hint. The wave function has to be continuous. That's one of them. So how does continuity help us? So I want no sudden jumps in the wave function, right? And we know that our wave function is 0 outside of the potential well, right? So what does this tell me about what the wave function should be at the positions x equals 0 and x equals L? Wave function should still be 0. So whatever the wave function does in between, it still has to like end up at 0 as it reaches the edges, right? Wave function's got to be continuous. So it can't like do this and then, you know, suddenly be 0 outside. That's not allowed. So so condition 1, continuity. So continuity of psi implies that psi of 0 equals psi of L equals 0. So what does this tell us about our coefficients A and B? So think about the psi of 0 one. Plug in x equals 0 into this equation, and what do we get? You want to say that again, but slower? So, all right, let's do it slower then. Psi of 0 equals A sine of 0 plus B cos of 0. What's sine of 0? Sine of 0 is 1. Sine of 0 is 0. What's cos of 0? 1. All right. This is something you need to be on top of in university physics. You need to be on top of your trigonometry. Great. So psi of 0 is B. But we want psi of 0 to be 0. So what does this tell us about B? B equals B is 0. Good. So our wave function, therefore, is simply psi of x equals A sine of kx. So that's nice, right? Because sine starts at 0, it'll start at 0. Yeah. And that's good. Now, we have another condition to chase up, right? So you know that sine of x, right? It starts at 0, but it can like go up to be like this, right? Or it can go up faster and do this, right? But the point here is, right, there's only going to be, right, you want your sine to be in such a way that it ends up back at 0 at the other end, right? So you need very particular values of k in order to make this work, right? In order to have a solution. And since k is root 2 me, this tells you that only very particular values of e are going to work, right? So let's try it then. Now let's check out psi of L. So we have A sine of KL. I want this to be, what do we want psi of L to be? For what particle? Well, we only have one particle that we're talking about here. The electron, yeah. The particle in the well, which according to the question is an electron, but it couldn't be any particle, right? So what do we want psi of L to be? We want it to be 0, right? By continuity, because it has to be 0 because there's nothing outside the well. So we have A sine of KL equals 0. So, all right, now this is going to be another tough trigonometry question, right? What does this tell us about KL? So we want A sine of KL to be equal to 0. So KL can be 0, but then that's not a very interesting function because then it's sine of 0 times x. So that means k must be 0 because L is definitely not 0. So if k is 0, that's a very boring function because then we have a times sine of 0 times x, which is a constant function. In fact, no, it's a 0. It's plain 0. So are there any other values of KL that will make sine of KL 0? $180? Oh, very good. Yeah. So what about, so 180 in terms of radians is pi, right? What about 2 pi? 2 pi, so 360, you go back to 0. What about 3 pi or 4 pi? So right, sine of x goes like this. So here we have pi, 2 pi, 3 pi, 4 pi, and then of course we have minus pi, things like this, right? So KL can actually be a lot of things. So let's work it out, yeah? So the condition that the function has to be 0 at the other end tells us KL. Now the way to be most general about this is it's equal to pi times a number n. So where n can be ... up to -1, 0, 1, 2. So it can be any positive or negative integer or 0. Yes. So yes, it turns out you're completely right. So we will have to cut it off at 1, 2, and above. So 0, -1 won't work. But so far, this condition doesn't tell us this. We only have this to go on so far. So KL must be pi n. So we saw above that K is root 2 ME. So we have root 2 ME over H bar L is equal to pi n. So if we square both sides, we get 2 ME L squared over H bar squared equals pi squared n squared. Yeah. Which tells us that the energy must be pi squared. I'm going to put the n out the front. H bar squared over 2 L squared. So, which is n squared times, let's call it E1. So, you heard that in quantum mechanics, you said at the start, right? Things get quantized. You can only get certain values for things. And here we see our first example of quantization. And in classical mechanics, if you put like a marble in a beaker or a well or whatever, it can have any like kinetic energy it wants, right? But in quantum mechanics, you don't get that. The energy of the particle can only be certain values. These certain values. So isn't that kind of crazy to think about? No. You don't. So the idea is you have certain energy states. You have a ground state, which is the lowest energy state. So lowest energy. Actually, it'll be n equal to 1. Lowest energy is the E1 state, and then you have excited states. So you can give it energy, but you can only give it certain amounts of energy. So it has to be like this or this. So if you draw the energy like on a plot, you'll have E1, and then you'll have E2, E3, right. It's right. It's not continuous anymore. So, but you have a good point. So anyway, I'm not going to write my psi in terms of the En from now on, because this is an ugly expression to write out every time, and I don't want to do it. So we'll just keep writing it as A sine KL. It's almost done. We know that the energy is quantized. We can only have certain energy values. We still need to work out A. Actually, before I do that, let's actually plot our functions. E1. So we have psi of x is A sine kx, and I said I wouldn't do this, but which is A sine of pi n pi n x over L. Oh, I've made a mess of that. Pi n x over L. And I'm just using this condition here for K. Right. So we know that only certain values of n are allowed. So let's actually plot this, yeah? So it turns out for n equal to 1, so the lowest energy state, the E1 state, if you plot this, it'll look like this. The n equals 2 state, if you plot this, it'll look like this. So n equals 3, n equals 4. And you'll get something like something like this. And the red lines are your wave function, by the way, just to remind you, psi of x. So that's what your wave functions look like. And you might be asked to do this in an exam, right? Because this is a rather elementary function, right? With a bit of effort, you should be able to figure out how they work. And it makes sense, right? Because we made the constraint that it has to be 0 at this end and 0 at this end. So it kind of makes sense that the last energy state is the one that like hits 0 first. And then the next highest energy state is the one that crosses 0 once before crossing 0 at the end. And then the n equals 3 state crosses 0 here and crosses 0 here. And then, right. So it kind of makes sense that it starts crossing more and more times as you like raise up n. So question, what does the probability density of these wave functions look like? Exactly. It's the probability density, which is psi of x squared. If I were to plot it, it would probably look something like this. And so the interesting thing is, when you look at this, is that when you give your particle energy, more energy, the places where you're likely to find it and the places where you're unlikely to find it shuffle around a bit. So in the lowest energy state, you're very likely to find it somewhere in the middle. But if you give it a little bit of energy and you put it in the n equals 1 state, you're actually never going to find it in the middle, because the probability density is 0 there. And so you're more likely to find it a little bit to the left and a little bit to the right. And then as you increase the energy more and more, right, you can start drawing your own conclusions. So this is another aspect where quantum mechanics gets really unintuitive as well compared to classical physics, because you can never imagine, a macroscopic particle having behavior like this, right? If I put my marble in my jar, no matter how much energy I give it by swiggling it around, there's still a chance I can find it anywhere. But in quantum mechanics, no, if I give it a certain amount of energy, there are some places where I'll never ever find it. So, which is pretty whack. But oh well, that's how quantum do. Yes. Yes.
Where they've given a very similar equation, except that instead of that, it is n squared s squared over 8n s squared.
Is there also a pi in there?
No, there is not pi.
Ah, well, there you go. Is that what? Not quite, but I know what the problem is. The problem is that h bar is equal to h on 2 pi.
Oh,
So I have it written in terms of h bar, the reduced Planck's constant, and they've written it in terms of h. So the Schrodinger equation that I gave up here, I have it in terms of h bar. In your lectures, you might have seen it in terms of h. So you'd have an extra, instead of h bar squared on 2m, in your lectures, it might look like h squared on 8 pi squared m. But yeah. So they agree, but I've just used different symbols.
where they said I is equal to MEE.
I is equal to.
What exactly it means.
That is not an equation you have to deal with.
Oh, all right.
That looks like a solid state equation. And I think that I there is probably some kind of current, maybe.
Are you sure we shouldn't be concerned with this?
Well, if you just see an equation in your formula sheet and you've never seen in your lecture notes, just don't worry about it.
All right. Okay.
Yeah. And you said something about the time independent Schrodinger equation.
That was what we've been covering, but there is another one which is time dependent, which is a times e to the power negative blah 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 blah.
I'm basing it off the tutorial book.
Yeah.
My tutor wasn't able to answer this question about why U should be uniform and constant.
One the tutorial question.
So what's the setup here?
Most of this is
Wave function of particle, space dependent, doesn't need to be real, no. It's possible to determine it from measurements, no. Probability density, okay. Non-relativistic particles, particle moving in the x direction into a region where a potential relationships. Force is minus du dx. Physically, why do we need to make this assumption about u? Otherwise it's too hard to solve. Because right, e minus ux in terms of, yeah, because if u depended on position, right, then the wavelength would have to also depend on position. Because if the left hand side depends on x, then the right hand side also has to depend on x. And so it doesn't make sense to talk anymore about a fixed wavelength. Yeah. Anyway, we call this the time independent Schrodinger equation because we have no time derivatives here, basically. But it turns out you can write a time dependent one where you have the time derivative of the wave function. So you figure out how the wave function changes, but you don't need to know it in physics 1b. You do not need to know the time dependent Schrodinger equation.
I have another question. What's capital Z standing for over here? I understand this is the lowest energy state for an electron.
Z is atomic number. So that's the number of protons in the nucleus.
Right.
So these are the energy levels for electrons in a hydrogen atom.
Right. So if you take another element,
yes. Basically, because if you stick another proton in the nucleus, you're going to increase the electric potential because the electric field is going to get twice as strong.
That makes sense.
So the energy levels will depend on that.
Got it.
Yeah. And yeah. Anyway, you will see how these energy levels are derived in the third year quantum mechanics course, PHYS1231. Energy levels of the hydrogen atom. And it's basically the same thing. You're solving the Schrodinger equation, except instead of a finite square well like this, you're solving it where your potential is just the Coulomb potential. That you're familiar with from electromagnetism. Okay, you're gonna follow me back around. No, it's lost me. Okay, so yeah, right. oh, now it's following me, see? If I move, it turns to face me. Aha, how good. Okay. Yeah. So to recap, what have we learned from solving the Schrodinger equation for this finite square well? We've learned that we have to use certain conditions like continuity of the wave function, and continuity of the wave function gives us that our energy levels and therefore the states that our particle is allowed to be in are quantized. So they can only be certain discrete values. Say again. So it's always going to be, yes. So if they give you the square well from x equals minus L on 2 to L on 2 instead of 0 to L, it gets a bit harder because you can't throw away the cos one anymore. So that's why it's always easier to have it going from 0 to L instead of minus L on 2 to L on 2 or something like that. Oh, they asked that exact question. How good. Anyway, so depending on the energy that our particle has, its wave function will look like something like this, and its probability densities will look like something like this. So if we're happy with this, we only have one more loose end in our function, and that is, we still don't know what A is. So do we have any other physical constraint that we might be able to use to tell us what A is? I'll give you a hint. Think about the probability density. So, when you add up the probability of finding the particle everywhere, okay, or rather another way of putting it, what's the probability that you will find the particle inside the box? 1, right? Because you're always going to find it somewhere inside the box. So how do we express that mathematically? The condition that we will always find it somewhere inside the box with probability 1. So what we do is we take the probability density, psi of x squared, and if we integrate it over the box, 0 to L dx, this should be 1, right? So when you add up the probability all over the box, it should be 1. So I can plug it in, and so I have 0 to L, 1 must be equal to a squared sine squared pi n x over L dx. All right. Now, do you believe me if I say that this integral is equal to a squared L on 2? So there's an easy way and a hard way to do this integral. Do you want to know the easy way? This what? So the hard way to do the integral is you have some like weird identity where like, you know, cos of like 2x is something like, I don't even know, a half minus a half sine, or maybe it's sine squared x equals a half minus a half cos 2x or something. So if you substitute this in, right, if you integrate a half from 0 to L, you get L on 2. And if you integrate cos of x from 0 to L, it turns out you'll get 0. Because it oscillates between positive and negative, so that it'll cancel itself out. Okay, so that actually wasn't that painful. But the easy way is to note that sine squared plus cos squared equals 1. And so when you integrate from 0 to L, 0 to L, on the right-hand side, you'll get L. And on the left-hand side, it turns out, as long as you integrate over a friendly number of cycles, sine squared and cos squared will contribute evenly, the same amount. So the cos squared contribution is the same as the sine squared contribution. So it's actually just twice 0 to L sine squared. So therefore, integral sine squared is just L over 2. So that's the cheap way. You just go, all right, it's sine squared of some nonsense, but I know that my sine is behaving nicely within this region. So it's just going to be half of this. And the region is just because sine squared plus cos squared is 1. So that's the cheat. That's a nice little cheat you can do. But I don't know. I do not use this cheat often in life. It's in rare occasions like this where I get to. Huh. So anyway, we've done our integral. Huh? Well, it depends on if you're asked a question where you get to. Yeah. So anyway, we've done our integral, and it's equal to a squared L on 2, and we know that must be equal to 1. So this tells us that a squared is equal to 2 on L, or a is root 2 on L. So therefore, our wave function, finally, we've gotten there, psi of x is root 2 on L, sine pi n x over L. Oh. So yeah, so this factor in front, we call it a normalization constant. So we normalize our wave function so that the total probability of finding it inside the well is 1. Yeah. So we've had to put a lot into this. We've got our wave function and life is good. Yeah. So just one more remark, right? We need to rule out the negative n's and we need to rule out n equals 0. So if n equals 0, that's easy to rule out because that means our function is 0. And that's unphysical because then the total probability of finding it anywhere is 0, which is nonsense. Now, if n is a negative number, then this doesn't change the energy because if n equals 1 or n equals minus 1, because we're squaring n, it doesn't change anything. The only thing it'll change is, so it won't change the energy, but it will change the wave function because if we replace n with minus n, right here, then it'll change our wave function from the red ones to the green ones. Ah, why is that so thick? Something like this. But is this a problem? Is this actually a problem? So does this actually rule out the negative n's? It's what, sorry? Yeah, so it's still perfectly valid solutions. So what this reveals, what is
n represented when it's negative?
Exactly, good question. So what we have is that, so this state here has the same, so the n equals 1 state also has the same energy as the n equals minus 1 state. And the n equals 2 state has the same energy as the n equals minus 2 state, and so on and so forth. And when you take the probability density, which is absolute value squared, they both give the same probability density because one's just the negative of the other. So what this tells us is they're physically equivalent. N equals 1 is the same as n equals minus 1, and n equals 2 is the same as n equals minus 2, because they have the same energy, same probability density. So what this reveals, in fact, we can say something more general, and that's because we're taking the absolute value squared, actually psi and psi times e to the I alpha, so any complex phase, right? These will both have the same probability density, right? So there's actually a non-physicality, a little bit of non-physicality to the wave function in that you can slap on any complex phase So -1 is a complex phase, right? Because e to the I pi is -1. So that's one instance, is unphysical. So, so it doesn't matter if someone presents you a wave function and said, this is what I worked out for the exam, and you look at your one and you've got like a factor of I in front or a factor of -1 in front times their solution. That's fine because they're physically equivalent. So this is a a freedom in your wave function, and it implies, right, you can never directly measure your wave function. You can only ever measure like probability densities. So this phase is completely physically meaningless. You cannot measure the phase, it's unphysical. So yeah, so the n and -n solutions are the same because they just produce a phase, so we're good. We have no problems. Yeah. And it's the same way that a potential energy is not physical, right? Because when we talk about gravitational potential energy, we say it's mgh. But where are you measuring h from? You're measuring it from the ground. You're measuring it from the center of the earth, right? So the gravitational potential energy is not physical because you can add any arbitrary number to it. All that matters is its derivative, right? The difference in potential energy between points, but the absolute value doesn't matter. I can't resist saying this. This gives us a peek into the grand physical principle of what we call gauge invariance. So you have some physical quantity like a gravitational potential or a wave function where the physics is unchanged even if you modify it for a bit. So the gravitational potential doesn't change even if I add like a constant to it, because the difference in gravitational potential between points is all I care about. And the wave function doesn't change. The physical wave, your physical system doesn't change even if you put a phase on your wave function. And it turns out the fact that you can do this, you have a little bit of freedom with what you make your functions. And it turns out if you follow this through, you can actually come up with electromagnetism out of thin air. You can come up with all of Maxwell's equations, everything, from this principle that you can just add a phase to your function. Which is crazy. This is whack. The principle you can just add a phase to your wave function. Okay, you need to do a bit of fancy maths, not too fancy, but you need to do it, and you follow it through, and you get all of Maxwell's equations for free. This is awesome. This is really cool. So this is something you might see in third year if you take PHYS1231, particle physics in the early universe. But until then, just trust me. Trust me that this awesome thing, you get it for free just from the fact that the phase of a wave function is meaningless. Crazy. Okay. All right. So all of this is let me go back to the question. So part one was sketch the form of the wave function in the ground state and the first two excited state. We did that. We sketched them. So n equals 1. N equals 1 is the ground state. So the ground state is the lowest energy state. And the first two excited states are n equals 2 and n equals 3, because those are the next two after the ground state. So we're done. So question one, my answer to question one would look like whatever is in this box. And then maybe some working if I needed to, remember what the wave function looked like. So part two, to do some practical quantum mechanics. A friend comments, it would be amusing to think about a quantum Mr. Miyagi. So Mr. Miyagi is the sensei in the Karate Kid movies. Someone so skilled in martial arts, because in the movie he's like a fly's buzzing around, he has his chopsticks and he catches the fly. I think that's how it goes. So he claims that he has some, he can catch the electron on the first or second go with his chopsticks. So assuming that chopsticks are centered at the center of the well, 0L. So here we have some chopsticks. How many attempts would you know that quantum Mr. Miyagi is expected to have caught an electron in the second excited state, even if he has no real skill catching electrons at all? All right, so. Huh? Right. So you substitute n equals to 3 in what equation? So first of all, what I want, so he said have a capture width of 2 picometers. So what that means is, oh, where'd my undo button go? Is I have some area in the center here, centered around L on 2. So this point here is L on 2 minus 1 picometer. And this point here is L on 2 plus 1 picometer. And we want to find the probability that we will measure our wave function within this region, yeah? So can you dictate to me an equation that I can write down in terms of psi of x that and just leave it in terms of psi. We don't care about it being sine of whatever. Can you give me an equation that'll give you the probability? So the probability that I find the wave function between L on 2 minus 1 picometer equals what? So I'll give you a hint. Remember our statement earlier that the probability that a particle will be found in the entire well is this integral here. Integrate the probability density from 0 to L. So if I want to find it between these 2 points, very good, exactly. So the probability I'll find it in this area is integral from L on 2 minus 1 picometer to L on 2 plus 1 picometer of psi of x absolute value squared dx. And it says the second excited state. So the second excited state is, oh boy, root 2 on L sine of pi n x. Okay, so second excited state psi 2 of x is root 2 on L sine of 2 pi x on L. So this looks like an integral that I really don't want to do. Yes. Why I have to take the what? Integral. Because I'm wanting to find the probability that I'll find it in a region, right? And also it doesn't make sense to say the probability that I'll find it at a particular point. It doesn't make sense to talk about the probability to find it at one exact point. You always have to talk about probability densities, right? I can't just sample a density a single point and be like, you know, because like if my probability density is, you know, it looks something like this, right? And if I take the absolute value squared, it looks something like this. And if I just evaluate at the middle, it'll come out as something like, you know, exactly 2 on L, yeah? Because I square this and I get at the top of the sign, it'll come out as 2 on L. So if you say that the probability that I will find it at the very center of the thing is 2 on L, I'm going to say that's nonsense. Well, first of all, what's the units of 2 on L? 1 over length. Why can I have a probability that I measure in units of 1 over length? Nah, not gonna happen. So if you have something in units of 1 over length, it's basically begging for you to integrate dx to fix up the units. Or at least to multiply it by something that has units of length. So anyway, yeah, so basically, yeah, probability densities, right? It doesn't make sense to talk about the probability of measuring at a specific point. You have to talk about integrating over a certain region, basically. So anyway, I'm very lazy. I don't want to do this integral, so I'm going to make an approximation. I'm going to say, since this region is so like -1 picometer to 1 picometer is such a small region, right? Compared to the length of the well, I'm going to say this integral is approximately equal to psi of x at, psi evaluated at in the middle of the well times 2 picometers. So if I pretend my function is constant within this region, then I can pull it out the front of the integral. Yeah. And then the integral of just nothing from this region just gives you the width of that region. So hopefully this is like, in an exam, look for opportunities to make approximations like this if you can. Because it'll save you so much time. Yeah. Oh. And then anyway, I can just plug in, right? And this will come out to be, 2 on L sine of, well, I know that sine squared at the peak in the second excited state will be 1. So that just gives 1 times 2 picometers. And then I can just plug in with my calculator. Do we have a calculator? Yeah. So what's a picometer again? You have milli, micro, nano, pico. So it's 4 times 10 to the minus 12. 0.6 times 10 to the minus 9. One over 150. What's that as a decimal? Zero 0.00666. Oops. 0, and I'm just going to round to 7. Huh. So tiny. Mr. Miyagi sucks. He has a very tiny probability of measuring the particle here, basically. Huh?
This is also with respect to other specific type.
Specific type?
Yeah, because we love to know the motion.
No. So the great thing, it turns out, is if this is something I didn't mention actually, but it's a point that's worth making. Is when a quantum particle has a very specific energy, it will not move. It will not move. Okay. Okay. I'll talk about, so in order to talk about moving, we need to talk about time dependence, yeah? So I'll briefly talk about the time dependent Schrödinger equation. Okay, just watch. So you don't need to know this for exam. This is like a quick 2-minute explanation. The time dependent Schrödinger equation is this: I h bar d psi dt equals energy times psi. So I can solve this and I get psi of t equals psi times, or psi of t equals 0 times e to the minus I e t over h bar. Now, what did I tell you before about a phase? So these both have the same probability distributions. They're equal. So what this means is, so our wave function as a function of time is really this, and then I'll put in an extra factor of e to the minus I e t over h bar. But when I plot the probability density, right, it won't change at all. So if I start off my wave function in the, n equals 3 state, or in the ground state, or any other state, it'll stay like that, and its probability density will stay like that forever. So in the n equals 2 state, right, I will never find it in the middle of the well now and for the rest of time. Never, ever, ever. So that's the crazy thing. It just won't. So remember, okay, don't think about it as the electron traveling left and right. The electron is the wave function, and the wave function just looks like that. Right? Remember, in quantum physics, particles are not like little balls that, move around and bounce off walls. Particle is just a wave function. It's just sitting there as a standing wave for all eternity. I mean, of course, if you try to measure it right, then you knock it around, you perturb it, right? And sure, if you try to measure it in one spot, then you will change the wave function. All right. So what I say is not true if you mess with it, right? But if you just leave it, right, or you get, a million electrons and you get them all set up in the, n equals 2 state, and once a year you try to measure, the first one in the middle, and you measure the second one in the one as well, you'll never measure any of them in like that, minima spot. Okay, so yeah, your quantum state is ruined once you make a measurement, but if you have, duplicate ones set up, then you're good, right? Those ones will stay in that state until the end of time. Yeah. So, yeah. So, anyway, the rest of the question asks, how many attempts would you need to be certain that he's quartered? But you know how to do that, right? Like the probability, like after, let's say, after n attempts, the probability that he's not quartered is, 0.993 to the n. So the probability that he's quartered equals 1 minus 0.993 to the n. So if you want to be, very certain that he's caught it, you can say, all right, let's make that, 99%, and then figure out what n should be. And you'll find out that he's, he's got to try like 100 times before he gets it, because the probability is very low. Huh. But anyway, yeah. All right, so that's quantum. And it's taken me an hour and 50 minutes to go through one question in this exam, but that's okay, because we've learned a lot about how quantum mechanics works. So what do you want to go over next? Or do you have more questions about this that you want me to elaborate on? Like anything that's not making complete conceptual sense? Huh?
Did anybody else pop up online?
Videos pop up online, did you say?
Did anybody else pop up online?
There was one person who showed up at the start, but then I think she left after I started going on about quantum for a bit. So, oh well, that's okay.
Sorry.
That's okay. I prefer speaking with people. She didn't say anything anyway in chat, so I had no way of knowing what she was after.
I joined the 2111 just for a second. I was like, oh, I'm curious.
That's okay. This time next year, you'll be very confident in it. It'll all make tons of sense.
Next, so 2-on-1
Classical mechanics and special relativity. Very good.
Any advice?
Attend lectures, do tutorial problems. you know.
How will labs be? I'm pretty sure there are labs for high value physics as well.
That's okay.
Not really sure.
That's okay. How do labs work though? Each week you get assigned a lab. In the higher year labs, you'll go in, you'll get 3 or 4 hours to do your experiment.
4 hours.
Yes. Collect all your data. You know, you'll get like a big a big kid lab book. You have to, you know, structure it yourself, do the pre-work, you're not just given like a first year lab manual where, you know, just fill out the boxes, right?
Yeah.
You have to write everything yourself. And then to get marked, you have interviews with, it's a one-on-one marking session with an academic. So you'll sit down in a room with them, you'll show them your lab report, and you have to convince them that you know what you're doing and that you did a good job of it.
4 hours weekly.
Yeah, so yeah.
Is there a fixed account?
Oh, no, not weekly. In most courses, you only have to do like 2 or 3 experiments in the term.
Oh,
So how to probably work, I think, is you go in, you have 2 hours one week, and then the next week you'll have another 2 hours to finish off the experiment, and then the week after that you'll get marked.
Okay.
And then after that you'll do the next experiment, I think. Maybe, if I got my fact, it's been a long time, so I might not have my facts straight, but it might go roughly like that, right? You'll either do it all in 1 week, you'll have it spread across multiple weeks, and then either way, the week after you do it will be the week that you get marked.
Do we ever fix the academic who actually?
Nah,
some-
it'll change each time, probably.
Okay. Yep, that answers all my questions.
Yeah. Cool. Haha.
Wait, do we have access to this again?
No, but I can share the PDF.
We do. But I'm assuming this is covering a lot of past papers, like
So-
different fields.
So this is the 2019 past paper, right? Maybe. Actually, it might not be 2019. It was 2022. So this was the exam that like Anna and Kyle and whatever everyone did last year. Anyway, if we don't know what we want to go through, I can just we can look at the questions and you can tell me if you feel confident with this, or if you're like, this is boring. Next question. Oh, last question's bad though. Don't pay attention to the last part.
Very straightforward. Like, these are the straightforward questions. So it's all right.
They're normally rather straightforward, but they're tedious. Because you've got to add up the potential energy from like 4 things. And yeah, you just have to be careful not to make any mistakes with your signs or yeah. Okay. It's very tiny up on that screen. I'm sorry. Make it as big as I can.
Even the shade of regions are different.
Yeah, so it's metal. I think, would one of you like to come up and try drawing the potential as a function of radius? Do you think you can get it quickly and easily?
Yep.
So okay, we'll make this just a nice graph, right? Vertical position is the electric potential. V is a function of R, and we'll exactly draw it as a function of this R.
So that's something between 0 to 1.
So yeah, so you're gonna have to fill this in as a function of R. Like, it doesn't have to be perfect, but like sketch roughly what you think it'll be. You don't have to do it in one continuous line. If you think there's, you can get certain regions, you can fill them in, and then we'll critique you to see if you got it. Oh, actually, no, not the potential. The electric field. Sorry. Pretend the vertical axis is electric field, not potential. Oops. Don't worry. Just pretend. Like, in the there's a back button here, and you can also change to eraser here. Oh, I changed to eraser. Whoops. All right. All right. Whoop. So what do we think so far? Okay. Is your electric field? Yes, yes. So, so can you explain why you have it going down and then up again in some places? So, if you were to work out numerical expressions for the electric field, what equation or law would you use? What? No, don't look. Need you to tell me. This understanding comes from inside the brain, not inside the formula sheets. Right? Okay, that's okay. So, okay, if you don't remember the equation, can you tell me just what law you'd use? What physical principle would you use? Gauss's law. Very good, because to get the electric field at any point, you'd look at, the enclosed charge in a spherical shell.
On the charge.
So we're not talking about forces here, we're talking about electric field.
Right.
Gauss's law. No, stay up here. Oh, you can whatever you're more comfortable with. Tells us that if you have some distribution of charges Q, and you make a Gaussian surface around it, then if you integrate over your surface, which I'll call S, then E dot dA is equal to the enclosed charge, Q enclosed, over epsilon naught.
Right. Now I remember it.
Permittivity of free space. Right. And the great thing about Gauss's law is that it's applicable in situations with lots of symmetry. So if you know that your electric field, for instance, is the same magnitude all over your surface, then it becomes a constant that you can pull out of your integral, and you just get E times A equals Q enclosed of epsilon naught. So this is when you want to use Gauss's law, when you have lots of symmetry that you can abuse. Okay, so basically how we're going to do this is you're going to consider like various Gaussian surfaces, like here and here, here, whatever, right? To figure out what to figure out yeah. Jeez Louise. All right. Now. Okay, I'll leave those. Huh. Okay, so okay, so with Gauss's law in mind, or do we want to swap over and I don't want to force either of you to participate if you don't want to, but
It's not supposed to be, if I remember correctly, this one was 40H, it's not supposed to be constant between 230. It's going to decrease, right?
Huh. Um, all right. Okay, I can work through this from first principles with you both then. So I apply Gauss's law, yeah? And these are spherical shells. So what shape would I use as my Gaussian surface? Sphere. Great. So suppose I have inside my sphere an enclosed charge Q. And my electric field is constant, so I pull it out and I get this. For a sphere of radius r, what is A, the surface area?
Oh, I'm talking about the surface area of the sphere.
So, yeah. Huh?
I am unsure.
Yeah, it's 4 pi r squared. Yes, 4 pi r.
Yes, 4 pi r squared. Very good, because it's an area. It has to have units of length squared. So r squared. R squared's a good bet. So we have 4 pi r squared E equals Q enclosed over epsilon naught, or E equals Q enclosed over 4 pi epsilon naught r squared. So this looks a lot. So this looks a lot like the electric field for just like any odd point particle, yeah? But it works for any spherically symmetric charge configuration, it turns out, which is neato mosquito. So yeah, so yes, so out here, you were very right in drawing the electric field going down like this, because this is a like 1 on r squared. So this does indeed look like a 1 on r squared. Okay. So what we know is that, all right, whatever the charge enclosed in each point, it's going to go as 1 over r squared. So it's going to be like bounded by this dotted line. And if it's negative, it will be bounded by this dotted line. But now it's just a question of, right, is it 0 at points? Is it following along with this at points? Is it negative at points? Right? That's what we need to figure out here. Great. So let's do that now. Let's look at the charges, yeah? Okay, so let's work through it all together. Between a radius of 0 and r, what is the enclosed charge? Oh, so I've covered it up by my axes, but this outer one has a total charge on it of plus q. This one here has minus 2q. And this one here has plus q. So between 0 and r, so in this area here, right? What's the enclosed charge of my Gaussian surface? So my Gaussian surface will look like, you know, this, right? What's the charge enclosed by it? Plus, okay, I'm not asking for what E is, I'm asking for what the enclosed charge is. Plus Q. So plus, so I'm between 0 and r. So I'm drawing, this is my Gaussian surface. My Gaussian surface is within the first spherical shell. Is there anything that carries a charge enclosed within my Gaussian surface? It's 0. There's no enclosed charge, right? No enclosed charge. So that means the electric field from 0 up to big R, electric field from, so electric field from 0 up to big R is 0 because there's no enclosed charge that can produce an electric field. Now, between R and 2R. So inside the first shell. So if I make my Gaussian surface like this now, what will the enclosed charge be? Plus Q. So how do we know that all of the charge is on the inside of the cylinder? What if all of the charge plus Q is on the outside of the cylinder? Not the cylinder, sphere, sorry. Yeah. Yes, sort of. There's one other caveat. Have you heard in your lectures that inside a conducting material, there's no electric field? Right. So, so Gauss's law tells us the electric field is proportional to the enclosed charge. So that means if I make my Gaussian surface just still inside the sphere, that means there has to be no charges enclosed within my circle here, which in particular means there's going to be no charge on the inner surface of the sphere, the smaller, the one at radius R, and there's going to be no charge distributed like inside it like this. So already we know that the electric field all inside has got to be 0 up to radius 2R. So if there can be no charge on the inner surface or anywhere in the volume, where must the electric charge be placed? On the outside surface, exactly. So it's all along here. That's where the charge is. Why is this thick again? So the plus still too thick. So the charge of plus Q on the first sphere is all distributed along the outer surface, because it must be. All right. So we've got our electric field up to 2R. What is now, if I make my next Gaussian surface, between 2R and 3R, what will the enclosed charge be? I'll give you a hint. We have just determined that we have got the first shell has a total charge plus Q on it. So if we make our Gaussian surface enclosing that shell, it's just going to be plus Q. All right. So if the enclosed charge is plus Q, then the electric field is it going to be positive or negative? Positive. Great. So, and it's going to go as 1 over R squared. So it's going to go are we good? Very good. So now let's look at the region between 3R and 4R. So actually I shouldn't, we don't know if it's going to be 0 in here yet, so I shouldn't draw it coming down. So between 3R and 4R. Now, if I draw my next Gaussian surface, so first of all, we're inside a conductor now. So what should the electric field be? 0. So what should the enclosed charge be? Great. Now, we already have plus Q enclosed from the first shell, yeah? So if the enclosed charge has to be 0, what do we need? We need minus Q. Where do we need minus Q? On the inner surface. Does that make sense? Great. So on the inner surface, we must have minus Q. Minus Q. So that the enclosed charge would be 0, so that we get 0 electric field between 3R and 4R. Now, what must the charge on the outer surface of the second shell be? Huh? Why should it be minus Q?
The total charge in the second sphere is The shell is -2.
Exactly. The total charge on the second shell is minus Q. So if we've already got is minus 2Q. So if we've already got minus Q on the inside, we absolutely must have minus Q on the outside. So we have a minus Q here as well. Great. Now, between 4R and 5R. So I draw my Gaussian surface like this. What is my enclosed charge? Minus Q, because we have plus Q from the first shell and minus 2Q from the second shell. So is my electric field going to be positive or negative? Negative, because we have total enclosed charge minus Q, and it's just minus Q, not minus 2Q or anything. So it's only going to look like this. So it's not going to be longer like this or anything, or shorter. Right, now, easy question. What's the electric field between 5 and 6? 0. So what does that tell us about the charge on the inner surface of the third sphere? Plus Q. Very good. Plus Q. Great. So now what is going to be the charge on the exterior surface of the third shell? 0. Why is it going to be 0? Exactly. So whoosh, the electric field is going to be completely 0 outside. So there we go. So we just have to work through it in steps. We have to use what we know, and we just build up. We understand where the charge is distributed. So, all right. Oh my God, I used a really crappy color for the bright projector. I'm sorry.
In terms of the magnitude, looking at the slope for the electric field, how do we determine the magnitudes, or like how high it goes, or the value for the slope?
So the question doesn't ask. So you don't have to be specific about it.
Okay,
but if you want,
how do we draw that? How do we draw the line for the electric field?
so how do you draw it? So I went that. So we know that if for a spherical Gaussian surface, it goes as blah 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 1 over r squared.
Right.
So whatever it is.
Fields between two conductors.
Yeah. So whatever it is, it will depend on r as 1 over r squared. So all I did is I drew these dotted lines. This dotted line is a 1 over r squared function. And if you want, you can pretend it's a q over 4 pi epsilon naught r squared function. And so when my electric field is q over 4 pi epsilon naught r squared, I can just draw it meeting up with this line. And when it's minus q on 4 pi epsilon naught r squared, I draw it meeting up with the line, the negative version of it. Yeah, so this line is minus 1 on r squared. Well, it's proportional to. So I drew this very ugly. Like in the actual exam, you've got online exams, so I don't even know why we bother going over this, but yeah, in an actual exam, I would probably draw it as, I'd sketch out my 1 on r squared, and then, and then, I'd mark out r, 2r, 3r, things like that. Because of course, you can't draw on top of these things in the exam. Okay, so that's that. Point at me, please. Yay. All right, so that's that. Are we happy, or do we want to ask anything about Gauss's law in general, or? Okay. Do we understand how to work out magnetic fields with, say, the Biot-Savart law or Ampere's law? Or do we want to revise any of that? How much time do we have left? We have about 20 minutes left. And I'm out of strepsils, so I'm going to be coughing a lot more. I'm sorry. Huh? Sorry? Yeah, I've been sick since Sunday. But I came in here anyway because I didn't want to let PHYS1231. Huh? Yeah, I'm a. Oh crap! Yeah, I should have put my mask on when I came close to you too. It's probably okay. I'm getting less sick. It's just like a lot of it's a lot of phlegm that's building up in here, so I just have to keep coughing it out or it gets like uncomfortable. Yeah. I also had the COVID shot and the flu shot yesterday, so my arms feel super heavy and achy. Oh well. Anyway, so I'll go through the options. So we have this, and we can work out the magnetic field coming from this. There's a question about the change in magnetic flux if this thing rotates in a magnetic field. There's a question about basically Snell's law and refractive indices, but this one's a little bit complicated because you have to think of like two different refractions in one and like chain together multiple things that you know at the same time. So you can think about that. Sorry, what was that? Anyway, the question after that is another refractive index question, and it's like, how can you tell apart real diamonds which have this refractive index from fake diamonds which have another one? This is a long reading question, so I'll just skip over it. Sorry. This one talks about our two favorite telescopes, the Hubble and James Webb Space Telescope. And it wants to ask which is better for looking at certain things going on in the Earth and the Moon. So I'll just ask with us now. Question one, right? Part one, which would be the best telescope to use? Do you two know how you'd approach answering that? Oh, you might have discussed this one. So do you remember? Oh. So do you remember any criterions for determining if a telescope is able to lenses?
Yeah, lenses.
What? So you haven't learned Rayleigh's criterion?
If I remember correctly, our professor mentioned something about Rayleigh, but we haven't studied the criteria in our slides or lectures.
Oh.
I attended all of my lectures, but I heard a few.
All right. Okay. This time when I get close, I'm putting on the mask.
We haven't studied telescope or Rayleigh's criteria.
So it's
Okay. Yeah. This one's split, which they asked about polarizer.
What would this come under?
so have you done
Yeah, and that's
interesting.
Refraction. This isn't refraction and reflection, is it?
So you've done single slit.
we tackled single, double,
This
but
isn't
not too much on telescopes.
so too.
Okay.
Monochromatic and broad spectrum waves, interference and reflection, Young's level slit experiment.
Okay. Just for education then, I'll tell you the principle of it. Is you know that when light goes through a single slit, right? It produces a diffraction pattern that looks something like this. Yeah. So the idea is, if you have a telescope and you're looking at like two objects, like stars or whatever, and light will come through, the lens of a telescope is like a single slit. So what will happen is, one of the objects, this one here, will look like this, and the other object will look like this. And the idea is, if they're very close to each other, okay, if they're very close to each other, they'll look like this, so that the total amount of light you see is just this. And then you can't tell them apart. But if they're far enough away from each other, specifically, if the first minima of one of them is where the first maxima of the other is, then we say that then when you look at the total thing, they'll be just resolvable. So basically what you do is you work out how far apart they have to be in order for the maxima of one to be on top of the first minima of another. And you get that the angular separation of them, theta must be greater than or equal to 1.22 lambda over d, where d is the diameter of your slit, basically. That's the idea. So it's just applying single slit diffraction. In order to figure out if you can like actually tell apart. And this is relevant because you can like, work out the, distance between features in like letters on a piece of paper, and you can figure out, and if you know like the diameter of like the lens in your eye, you can figure out, how far apart, you can put the paper from your eye before you can't tell the letters apart anymore. Basically. So yeah, so that's the idea behind Rayleigh's criterion. But if you haven't learned it in your lectures, then don't worry about it. That was just a quick. So anyway, for this question, you'd work out the minimum angular resolution of each of the telescopes, and whichever one had the better angular resolution is the better one, basically, so that the smallest angle that it could discern. But anyway.
Wait, so how do you solve that question? How do you solve the question again?
Don't worry about it. If you haven't learned Rayleigh's criterion in your lectures, don't worry about it. I just want to give you a high level understanding.
It's a formula sheet.
Everything in your. Okay. So what you do is you pull out Rayleigh's criterion, which I wrote over there, which was theta 0.22 lambda on d. Okay, and this is your space telescope, and you're looking at some object on Earth or whatever, and that object has a width, which I will call capital L. And there'll be some angle theta from the top to the bottom of it, and if it's a distance r away, then we have that theta is approximately tan theta, which is approximately sine theta for small angles. Hopefully you know these approximations, which is approximately L over R. So R is your distance to it, and L is the width of the thing you're trying to look at. So we have L over R is greater than or equal to 1.22 lambda over d. And so we have L must be greater than or equal to 1.22 lambda R on D. And well, if it's on, so they say the object is on Earth. So all you got to do is plug in the distance to Earth. So capital R would be this. You've got to plug in the wavelength, which is somewhere between 100 nanometers and 100 micrometers. So what's a good number in between 100 nanometers and 100 micrometers? Yeah, just take an arbitrary one. So fairly uniform intensity between 100 nanometers and 100 micrometers means if I plot the intensity as a function of frequency, it'll look like from 100 nanometers to 100, something like this. Anyway, you just pick a nice lambda and plug it in, and then you plug in d as well, the diameter of this. And whichever one has a smaller L, it means it's a better telescope because you can look at smaller objects.
Oh, yeah. So it doesn't matter. So this shouldn't be affected by the lambda we use. So you can just take lambda as a constant.
Yeah.
And just compare the
Exactly. So does that make sense to you? Okay. Okay. And if I 1 4 meters 1. So it turns out if I plug the numbers in for Hubble, I get something like L must be greater than 0.14 meters, and for JWST, I get L must be approximately greater than or equal to 150 meters. So question 2 goes, there are two competing theories that it's 1 kilometer across or 2 small 100-meter sources a kilometer apart. And can you tell them apart with something that can see up to 0.14 meters? Yes, easily, because you can see a lot more precisely than you need to. And then it says if a second anomaly appears on the moon, which is best? And in this one, you just plug in the distance to the moon, and it turns out JWST would be better in this case. So yeah, that's Rayleigh's criterion. It's just, it's just things diffract when you put them through single slits, and that means you can't, you have a finite amount of resolution in your measuring devices. Okay. And then there was this question 6. So this is actually a quantum mechanics question. So, do we know how we'd approach this question?
Yeah, exactly. It's like, I'm gonna just aim all of the people go just type it next to each other. Put a couple of I'll leave it next to the sun, like the sun, and I'll add a bunch of magnifying glass. So they're pretty.
So the smallest dimension resolvable, we say, is approximately equal to the wavelength of the object. So we want to compare the wavelength of an electron to the wavelength of light. Yeah. So let's start with light. Yeah. What's the smallest wavelength of light that we can use? It's about blue light, right? It's about 400 nanometers, right? because visible light goes from like blue up to red or whatever, and red's like, I don't know, a couple hundred more. So now for an electron, do you remember the equation for its wavelength? So that sounds to me like the equation for the Compton effect.
Or you could just do H over the momentum of the electron.
So which one is it?
Do we have the momentum of an electron? Do we assume electron? We don't have the momentum of electron, right?
So it's asking you what energy do you need to make the electron have the same wavelength. So in order to get the electron to a wavelength of 400 nanometers, we have to figure out how much energy we have to pump into it. But
Yeah,
first,
so K mass is equal to H minus whatever it is.
all right, now you're just pulling out random equations here that you think you're not understanding what situation they're all used from, and understanding the situation is more important. So have we heard of the de Broglie wavelength or the de Broglie if we are uncultured?
I've heard of it.
That looked like whatever. Okay, I'll give you a reminder. This is one of the progenitors to quantum mechanics, and we discovered that electrons have wave-like properties if you look on small scales enough. Of course, we know electrons are described by wave functions, so electrons actually are waves. But so if an electron is a wave, it turns out the momentum relates to its wavelength as followed: h over p, which is h over mv. H over momentum. So h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. All right. So if we want to make this 400 nanometers, we have to figure out so if we want this to be 400 nanometers, we need to solve mv is equal to h over 400 nanometers. Yeah. So now, and we can plug in numbers. I don't know what you get. 6.626 times 10 to the minus 34 over 400 times 10 to the minus 9. And actually, do I have to divide out both sides by m as well?
Yes.
Okay. M is something like 9.1 times 10 to the minus 31 or something, if I'm right. Oh, how good am I? I'm so smart. Okay. Oh, what was that? Sorry. Okay. Anyway, we got a stupidly small number probably. What are we? What? I don't know. 1,000 meters per second.
It is small on an atomic scale.
Actually, no, 1,000 is probably reasonable.
Yeah, it makes sense on an
Yeah.
atomic scale.
No, I was wondering why was it bigger?
As long as it's more than the speed of light, then it's reasonable. Okay, so So let's say it's approximately 1,000 meters per second. All right, now, how much energy do we have to pump into this to get it to this speed? So what's the equation for kinetic energy? E equals a half mv squared. Now, if that energy comes from a voltage, how much work is done on, how much work does an electric field do? Do we know the equation for how much work an electric field does on an electron when it accelerates across a voltage?
Basically, the change.
Yeah, the change in energy. So and it's half. So where's the voltage come in? Not quite. Voltage has units of volts, not joules. ow. I will not. So for an electric field, right? Remember, work in general, work equals integral of force times distance. Yeah. So if the force is the electric force, it's integral of QE times distance, right? Q is a constant, so we pull it out. E dot ds. Do you recognize what E dot ds is between 2 points? So if I have a point A and a point B, and ds is, this vector, it is Q times the voltage difference between point A and B. Another way, you might remember that the electric field is given by something like dV dx, like or maybe it's minus dV. I think this is dV dx. Equals grad phi. Sure, we'll say it's dV dx. So you'll see that these two equations are complementary, right? The electric field is the derivative of voltage, and voltage is the integral of the electric field over a path. So, right, you just got to remember one, and you remember the other, and then life is good. Anyway, so the point is the work done by the voltage is equal to Q times the voltage difference. So if the energy, we want to give it energy half mv squared, all of this energy will come from the voltage, Q capital V. Except the charge of the electron, right? It's not just any old Q, it's E. The electric charge, little e. So this is not Euler's constant, right? It's the electric charge. So 1.602 times 10 to the minus 19 or something like that. So now you just plug in, right? And we rearrange capital V for voltage is equal to half 1 on 2e times m velocity, small v squared. We just plug in small v, we plug in the electron mass, which was this bit here, and E here is 1.602 times 10 to the minus 19. I don't know, what do you get when you plug that into your calculator? I'll tell you what I got when I did this last year. So I got something like 9 times 10 to the minus 6 volts. Is that in agreement? Like roughly to order of magnitude?
I think maybe I typed something wrong.
Times
Wait.
times 9.1 times 10 what times 1,000. Oh well, maybe I buggered something up. Who knows? Oh, because what you have typed in looks legit. Maybe I just goofed. I don't know, maybe we got the velocity wrong. Oh well, I didn't write down an intermediate thing in my thing. Oh, okay, whatever. Maybe that's the answer and I screwed it up here. Who knows? Oh well, sure. We'll say that your answer is what it is. Doesn't matter, right? Point is, we understand the concepts, right? We understand that electrons have a wavelength given by the de Broglie wavelength, which is h over momentum, lambda equals h on mv. And we just remember that the energy that you get from an accelerating across the voltage is the charge times the voltage difference.
The reason as to why the bigger number the using an approximate vector and the actual velocity is actually more than 1,000. It's around 1,500 volts. So that probably makes that up to get it 9.44 and we get it.
I mean, like I'm just like going off the number I wrote down last year. I didn't even work out the velocity in the intermediate step. Anyway, doesn't matter. Yes, because there's no way I'm gonna prepare a whole new thing, a whole new past exam to go over when I have PhD work to do, unfortunately. It's time efficient to recycle old stuff, but that's okay because we all learned stuff anyway, so you didn't know, so no harm. Anyway, holy crap, it's 4:10, so no. So all stuff I do for PHYS12, I do out of the goodness of my own heart, not because I'm being paid for it. So yeah, there is an upper limit to how much I can actually do before like it starts taking away from. But this is okay. Anyway, I should stop the Zoom thinger and wrap it up unless we have any last minute things we want to know or go over. Brewster's angle. Okay, sure. I can explain Brewster's angle. Oh, okay, so so if I have a charge, positive or negative charge, whatever, and I wiggle it up and down, it will create light or electromagnetic radiation that goes off in this direction. So I wiggle it up and down, and the radiation goes perpendicular to the direction I'm wiggling it. And it will be polarized in the direction I do the wiggles. So if I wiggle up and down, so right, the light will be polarized like this. If I wiggle it in and out of the page, the light will be polarized like this, but it'll still go off perpendicular. Yeah. So the polarization of light that I could produce by wiggling something depends on the direction I wiggle it. So wiggle it up and down, wiggle it this way. So now, cool things happen when you have refraction coming in. So imagine I have, say, water, and as we know, right, light can come in and it gets refracted. Now, why does light get refracted? Basically, it's you have the wiggles from your light here. It makes the atoms in the water start wiggling. And this wiggling will cause the light to move perpendicular to those wiggles, basically. So the wiggling like adds to the incoming light and interferes like in such a way that causes it to divert its direction. Now, well, let's imagine a very special case. Imagine I have my incoming light such that the and I set it up so that the reflected ray, so light, some of the light reflects and some of it refracts, yeah? I'm going to set it up so that the reflected ray is 90 degrees to the refracted ray. Now, remember what I said about the wiggling. So if the light is going down this direction, it means the atoms in the water have to be wiggling in this direction, right? They have to be wiggling perpendicular to the direction the light is going. Now you notice that the direction they're wiggling in is the same direction that the reflected light goes. Now, where does the reflected light come from? It comes from the wiggling of the atoms in the water, like creating basically light going in the opposite direction. But you saw that when I wiggle my atom, the light has to come out perpendicular to the direction of the wiggling. So if it goes up and down, the light has to come out this way. There is no light that comes out this way. So if my light wiggles up, if my atoms wiggle this way, no light comes this way, and light goes that way. So if my atoms are in the water are wiggling this way, I'm going to get no light in the reflected direction. But this is only for one polarization, right? I can have two polarizations. I can have wiggles this way, and I can have wiggles in and out of the page. So wiggles and then wiggles like this. So the refracted ray, and I've made a big mess of it, right? You'll get components wiggling like this, and you'll get components going in and out of the page. Now, the ones going like this, as I just argued, they will not produce any radiation going out. They will not contribute to the reflected ray because the reflected ray is in the direction of the wiggles. But the wiggles going in and out of the page, those are perfectly perpendicular to the reflected ray. So that can produce light. So what this means is, if you have a very special setup, if you're at a very special angle where your reflected ray and your reflected ray are at 90 degrees, only one polarization will get reflected. So only the wiggles going in and out of the page will get reflected, basically. So Brewster's angle, and you can, angle of incidence here, θ1, angle of, this is also θ1, angle of refraction, θ2. We have n1 sine θ1 equals n2 sine θ2. And the condition that the reflected ray and the refracted ray are 90 degrees to each other tells us that these three angles here, θ1, 90 degrees, and θ2, they have to all add up to 180 degrees. So we have we have θ1 plus θ2 is 90 degrees. So I can eliminate θ2. So θ2 is 90 minus θ1. Sine of θ2 becomes sine of 90 minus θ1, which is cos of θ1. And so Snell's law now becomes n1 sine θ1 equals n2 cos θ1. Or if I divide throughout, I get tan of θ1 equals n2 over n1. So when this is satisfied, I call θ1 Brewster's angle. So yes, true for every. Oh, it works for every medium. Every medium. But of course, there's only one angle that'll work, and it's this one here. One incident angle, Bruce's angle, given by tan of theta b equals n2 over n1. So yeah, so that's where it comes from. So do you understand the reasoning behind it? Yeah, you have to be at 90 degrees so that only one polarization survives because only it's perpendicular. And then if you work through that perpendicular condition, you get this. Theta b. Oh, I have to know what n2 and n1 are. So what it's saying is, suppose I'm in air, and this is water, and suppose I were to reflect light off at a perfect angle, this angle here, theta equals inverse tan of n of water over n of air. So if I do it at this exact angle, then the light coming off it will be polarized. The reflected light will be completely polarized. And you can see this because if you take sunglasses, a lot of sunglasses have polarizing filters. You can like look at reflections on like a lake or something, and you can tilt your head 90 degrees so you filter out the other polarization, and it'll like change the brightness of the reflection. Like some of it will go away and all that. So yeah. So hopefully that makes sense, and hopefully that makes sense, and I didn't like just spray too much information. Yeah.
I'm gonna explain it.
Sure,
Yeah,
thanks
yeah.
for being a lecturer.
We'll see. We will see. It's hard to do actual lectures because you have pressure to like just get through the content. It's so much easier when I have just like the two of you and your specific address questions, and I can like comfortably address you and like constantly bouncing back for feedback to make sure you're following along. But if it's like a bunch of people, it gets a lot harder. Anyway, yeah, I don't know. We'll see. Anyway, is there anything else, or are we good? Cool, awesome.
Will we have another revision session?
I don't think so.
No, this is the only one. No, thank you both for coming. It was a delight.
I was gonna like give away Kit Kats, but then you said so.
Oh.
I mean, maybe
It's okay. It's okay. You don't have to. You can take it for yourself.
have fun.
Just have it for yourself, but spread out over a longer time. Anyway, I should end the Zoom meeting. Bye, everyone at home, or anyone watching the recording.